calculate angle of departure and angle of arrival. Before that, whether do you have any possibility of having angle of departure arrival? So as in this problem, gh of s is equal to, so k divided by s into s minus 6 into s square plus 4s plus 13. Therefore, there is we have complex poles. Whenever you have complex poles, we need to calculate angle of departure. Let us see how to calculate it. So s is equal 0 one pole, s is equal minus 6 another pole, minus 2 plus j3, minus 2 minus j3. Let us take this pole, and from this pole you draw the vectors to minus 6 and 0 and also minus 2 minus j3. So when you draw the vectors, then you just name the angles. This angle is phi p1, this angle is phi p2 and this angle is phi p3. So phi p1 you can find it as 180 minus, we have tan inverse of 3 by 2, that will be you will be having 123.7. Then phi p2 is tan inverse of 3 by 4, 36.86, and this is directly 90 degrees. Therefore, all three angles are available. Then there are no zeros, therefore sigma phi z is not needed. So we substitute in the formula, that is phi d is equal to phi 180 minus and all these angles 123 plus 36.86 plus 90 degrees. When you substitute, and you will be getting phi d as minus 70.46. So minus 70.46 is the angle of departure at this complex pole, and 70.46 is the angle of departure for the bottom pole. So we know these two angles. So next, so once all the information is available, then we can sketch the root locus. We already seen that breakpoints calculations, and also we have angle of arrival. There are no angle of arrival, we have angle of departure calculations and imaginary crossover calculations also. So finally we will see how to sketch this, and we will say what will be the stability condition. So when you look at the sketch of it, 1, 2, 3, 4 poles are there, which means there are 4 root locus branches, and on real axis we have two poles, and there is one breakpoint which is minus 4.2, and similarly I have two complex poles. So in this case, the breakpoint and the centroid and angle of departures play important role when you are deciding the sketch of the root locus in this case. Now look at the asymptotes, and the centroid is at minus 2.5, and one is A1, A2, A3 and A4. Now where is the breakpoint? Breakpoint is away from the centroid, away from the image, that means towards the left direction. It is minus 4.2. Minus 2 point is a centroid, minus 4 point is a breakpoint. So for the pole which is at minus 6, the pole which is there s is equal 0 will come together to minus 4.2, and they enter into the complex plane, because that point is the breakpoint. Once they enter into the complex plane, it should look at either 0 or nearest asymptote. The nearest asymptote is A2, therefore it will go along with this to infinity, and this will go along with this to infinity. Then what about the first two complex poles? So we have angle 70 degrees around, so it takes the 70 degrees and it is going to infinity. It is crossing the imaginary axis. While it is crossing, then it takes that point, imaginary crossover point, and bottom also takes the imaginary crossover point. It goes like this. Now both are on real axis are coming, and one is going towards the left direction, whereas complex poles are going towards the right direction, and these two poles are responsible for unstable nature of the system. If at all, if this breakpoint is the other side, for example in certain problem, if this breakpoint is at minus 2.5 and your centroid is at minus 4.2, so in that case you will have, of course, the shape of 4 asymptotes will be same only, but when these two real poles they are going to minus 2.5, they enter into the complex plane, then they look at the nearest asymptote. In this case, your nearest asymptote will be your A1 and A4. So they go in this direction and this direction. So if at all breakpoint is nearer to the imaginary and centroid is away. But for this problem, your centroid is nearer to the imaginary and breakpoint is away. So the root locus for the real root locus branches, so real poles, they are going towards the left direction and complex are going towards the right direction. Then what will be the stability condition? We know at imaginary crossover point K is 227.7. That means the K range from 0 to 227.7, the system will be stable, and beyond 227.7 the system is unstable. Exactly K is equal to 220.7, the system is marginally stable, therefore you will get a critically stable condition or completely oscillatory response.